Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So, roughly a year and a half ago, I talked about understanding measure, ratio, and number. So, I want to clarify a few more things in this video and go slightly slower than I normally do so that those of you who are new to this can understand. Okay, so in the beginning, we dealt only with ratios of magnitudes. Now, a magnitude is not a length, it's not an area, it's not a volume. It's just an idea or a concept of size, dimension, or extent. Okay, it can be any of those things. It doesn't have to be length. It can be mass. It can be anything else. Okay, so the ancient Greeks developed arithmetic using ratios. In other words, all the four basic operations of arithmetic were done with ratios. So although they didn't know about what I'm going to show you now, it's not a long stretch to say that they could easily have known this because I've only realized these things by studying what they said carefully. And of course, the elements wasn't written down perfectly. So let me show you how they dealt with ratios and arithmetic of ratios. So if you have any particular ratio, let's say let's say you have the length of a circumference and diameter, right? Well, the way they could have dealt with it is they would have said, let's uh, plot, let's plot the circumference, all right, along this. I didn't mean to do that. Along the y-axis. It doesn't have to be a y-axis. In fact, these these lines here can be at any angle. All right. So let's say we've got it over there and we've got that roughly about there, say 3.1 something. Okay. Well, of course, in geometry, it's exact because we take a divider and we get the exact length there. Similarly, let's make this a real big one here so we can know where we're going, like that and like that. Okay. And now, and this little one here, we could say, okay, that's about 1, right? So we're going to put it over there and we're going to join them like that. Okay, so now I'm going to now just move the axis so I can make things easier for you to see. So how about I do that? Okay, and now we've got a clearer view. And now we can see what's happening here. If, for example, we want any proportional ratio to this ratio, how do we do that? It's actually very easy to do. So there are essentially two steps. The first step is we join these points like that. And the second step is that we place a point anywhere on the x-axis. Actually, there are three steps. We join these, we place a point on the x-axis, and the final step is to draw a line through this point here that is parallel to this line, right? So that's easy to do, parallel line. So we're going to draw a line like that, okay, and we're going to mark the intersection like so. Okay, and now we don't need that entire line. We can just hide it and join the segment. Okay, so we know these are parallel. Now, you can find any other ratio that is proportional to the circumference to the diameter, okay? Even smaller than the one that you find. And there are, as they say in the mainstream, infinitely many, or innumerably many rather, okay, ratios. And how do you know this? Because you can just if you wanted to have this distance for the diameter, then this becomes your ratio, and this becomes, that becomes your diameter, and this becomes your circumference. Okay, so I don't really want those. I don't want either of those. Okay, I'm just showing you here how you can have infinitely many ratios. All right. So if you wanted to manipulate ratios, different kinds of ratios. So I'm going to move away now. I'm going to use even numbers so you can see the effect, because it's hard to see the effect if you're using uh, values that don't have an exact measure. So now, what is the difference between ratio and measure? So if you've got this ratio here, 3 to 1, the measure of this ratio is 3 to 1, right? Just like that. It's written in algebra as 3 to 1, right? Or as a number, it's written as 3/1. Okay. Now, that is the measure of this ratio. Okay, so you've got lines. So essentially, you've got lines. You've got lines. You've got three, oops, 3 and 1. I didn't do that great, but you know what I mean. 3 and 1. And of course, you count, you use this consequent, you use this consequent as a unit, and you count up the number of parts in the antecedent. And there are three, right? So you can say there's one of the unit and three in the antecedent. Okay. So that becomes your measure. So that's why I always say that a number is a name given to a measure that describes a ratio of magnitudes. Okay. And that's the correct definition of number. Mainstream idiots don't understand that. They don't have it because they've never understood the concept of number. All right. So now let's just get that out of the way, and that as well. Okay, so now we know what is a measure of a ratio, and we can add ratios easily. So let's say we've got this ratio 3 to 1, and we want to add. Let's do another one. Let's say 5 to 4, right? So once again, we'd have to connect these points like so. And the only way we can add these ratios is if we have a common consequent. So since the consequents are not the same, right? Let's just leave that alone there for the time being. Don't want to move that. Okay. So the consequence here is 1 and 4. So we know that this guy here is a proportional ratio to this guy. So all we have to do is just move it on to the 0.4. And now the two ratios that we have the same consequent, right? And what are those ratios? Let's see, what are those ratios? So the first ratio will be 5/4, like that, 5/4. And the second ratio, which is 3/1, now is transformed to 12/4, right? So that becomes 12/4. So now all we have to do if we want to add, we have the one antecedent, the 12, and the other antecedent, the 5. So it's very easy to add them. We can just take a divider and extend this line by this line, and we'll have what? 17, right? If we measure it. But otherwise, we'll just have a line like that. And of course, that line by itself makes no sense unless we use the consequent, okay? So the consequent will be 4 long. So that's the ratio. Now, if you want to talk about this in algebra and you're adding them, you'd have to measure this ratio down here, this ratio, okay? And its measure turns out to be 17/4, okay? And you can also simplify that by saying that's 4 1/4. So, and what you've done here is you've assumed that 4 is the unit, and you've taken one equal part of the unit to express the sum of these two ratios. Okay, so you wanted to express the sum of those two ratios. Does that make sense? And of course, if you wanted to express the difference, you would take your divider and remove it off there. Okay, and now It's very, very much the same process with division. So because I've done too much here, I'm just going to clear this out and say new, discard. And over here, I'm going to say I want no new objects. That's correct. Okay, good. Now, let's get this back here. So let's say now that we want to divide, let's say 3/4, uh, 3/4. Okay, and let's join them up. We don't have to join them up, but I'll do it so you can see what's happening. Like that, 3/4. Okay. Actually, I said I don't want naming objects. Didn't I say that? No new objects? Yeah. So why is it naming them? That's weird. Okay. So odd that it's giving them labels because I didn't ask it to give them labels. No labels. Okay. Right. I'm taking a little bit of time, but bear with me. Okay. So now we've got 3/4 and we want to divide it, let's say, by 2/9. Okay. So that would be, let's just use a segment, 2/9. 2, like that, and ninths. Okay. So now we can choose, like I said previously, we can choose anywhere along the horizontal line, the consequent. We can either move, we can find something similar to 2/9. So let me just write that down. So our two fractions are, first of all, 3/4, our ratio, sorry, are 3/4 and 2/9. So we can either change 2/9 so that it has 4 as a consequent, or we can change 3/4 so that it has 2/9. Now, if we, let's say we want to change this so that it has 4 as a consequence. So we do the same thing again then, right? We would draw a line here at 2/9 like that, and then put a point on the x-axis, and then draw a line parallel to this line through this point, right? Parallel line, so it'd go like that, okay? And then let's just put a intersection point there like that. And now we could move this to 4, as you see there. Okay, get rid of that. So that over there now is the new 2/9. It's actually a ratio that is proportional to 2/9. Okay, that's just under 1 there. That's not exactly 1. Okay, it's 0.89. So this here is approximately, not approximately, it's exactly proportional to 2/9. So now we could also move. Now, what have I done here? Have I done that right? Yeah. So now we've got 3/4, which is over here. Let's draw a line through there. So we've got 3/4 and 2/9. Now it's very easy to divide them. So what we would do is we would take uh, the antecedent for 3/4, which is 3. Okay. So the antecedent for 3/4, which is 3, like that. It's this line here. And this antecedent for the 2/9, which we said is what? Which we said is roughly 0.89. Let's have some more. Uh, I want to have some more decimals. So if I go there and I say, now why am I not getting decimals? This is ridiculous. Oh no, I need to go to settings. All right, decimals, let's make it about 5 places. And let's see what this point here is. So this point here is G. So if you look at G, it's 0.489. And uh, if we say the Y, if we say this Y, 3, divided by the Y of G, like that, that gives us a result, right? Okay, so that means that 3/4 divided by 2.9, if measured, would give us this value here. So let's see if that's correct, if we've done everything correct. So algebraically, we would say 3/4 divided by 2/9, like that, which is the same as multiplied by 9/2, right? Okay. And then that would be 27/8. And what is 27/8? Let's just calculate that. 27/8. And that's the answer, right? 3.375. So that's the measure. 27/8. 27/8 is the measure of this ratio quotient. It's the measure. Now, if you wanted to say 3/4 multiplied by 2/9, then you'd leave this 3/4 alone, this 3/4 as you have it here, and you'd switch these two around. You'd have the 9 on this side and the 2 on this side. And then you do again a quotient, because multiplication is just a reciprocal division. Remember, division is the general measure of everything. So when you measure a ratio, you're actually using only one operation, and that's division. And of course, division uses either subtraction or addition, whichever you prefer. But you're using division to measure the antecedent with a consequent so that you can get a fraction. Okay? And to learn more about this, what you really need to do is you need to study very carefully my world renowned book called The Theory of Fractions for Dummies from book 5, where I explain all of these things and a lot more. And if you want to understand number and what it means, and you're planning to be a mathematician, this is the road to go. So I know I've been a little bit slow in presenting this, but that's okay because I want people to understand. So if you really want to understand number, this is the way to do it. There is no other way. Okay, you cannot derive number validly and systematically unless you do it this way. So that was, again, uh, a fallback to this video here, and clarifying some more things in this video, which was only 7 minutes, and I'm sure this one's going to be a lot longer. If you're not already a subscriber, become one, click like, become a follower, and tell your friends about this. And I'll be chatting to you hopefully about some other topic in the near future. I'm John Gabriel, and this is New Calculus Channel. Till next time, good.